All right, welcome back to the SciMax channel. Today we're going to talk about monotonic neural networks with uncertainty quantification in pycse. This is a part of a series that I've been working on of machine learning models that have properties you want. So not arbitrary fit anything kind of properties, but in this case, say you know you want a monotonic function to fit your data. That means it is continuously increasing or continuously decreasing in a monotonic way. And it turns out that you can create neural networks that have this property, and that is a benefit when you know that you want it, and you can guarantee that it's going to be. So this is done by putting specific constraints on the weights. We have non-negative weights so that we always have input to output. We can flip signs on the inputs for decreasing monotonicity. And then we use non-decreasing activations here, either softplus or ReLU. And that also guarantees in the end that we have monotonic behavior. Now, there's a few examples here. You might use them in chemistry, where we know the reaction rate can only go up with temperature, or economics, things that in medicine, materials, engineering, there's applications where we know something can only increase and can never go back down. And so if you get wiggles, then you might find that you violate something in thermodynamics, or you have unphysical behavior. So this is an example of a place where we would want to guarantee monotonic behavior. This is not a new idea. I certainly didn't make it up. There's some references here in the literature. You can see these are mostly from various NeurIPS conferences and other places. The final thing I'll mention is it turns out it's quite easy to add uncertainty quantification in here, and so here I use the LLPR, which I've used in a couple of examples before. It's especially easy to implement, and all of this, as with other packages like this that I've developed, were written with Claude Code to help me put it together. So I had it create this sklearn compatible JAX monotonic regressor, and I'll just walk through, how we use it. Here's where we import it. This line is just because I run this on Mac, and JAX is not fully supported with the Silicon GPU, so I keep it on the CPU for this. And we'll skip down through here and look at some data and a fit. So here are the two activations that are non-decreasing. We either have ReLU or you can have softplus. Either one is fine. It just depends on whether you want a continuous activation or a piecewise linear activation. And you can see here that if we have positive weights, we are only going to see positive outputs, and the functions are either decreasing or increasing continuously over here. So let's look at our first example, a monotonically increasing function. Let's just scroll down. Well, let's see what's in here. We have some data. This is something squared plus something, a little bit of noise. We make our JAX monotonic regressor with the hidden dimensions. Monotonicity equals 1 means it's increasing. -1 means decreasing. Some details about how many epochs to run. Here we use the fit and we get a score. And so eventually we get a low loss, low calibration, and a high R squared. And here we verify that all of the gradients are positive. And here's where you see the fit that goes through the data, and it's monotonic. If you had tried to do this with a regular neural net, you'd probably see wiggles and things that make it not totally monotonic. Here's an example for a monotonically decreasing function. So again, we make a model. This is something based on price. As price increases, demand decreases, and that is expected to be monotonically decreasing. Here we make our Jack's monotonic regressor and use the monotonicity -1. And this shows that all of the gradients are negative. And here we get the behavior that you expect for monotonically decreasing, and here you see the negative derivatives for the whole range. You can have mixed features, so we may have multiple outputs that we need to have. Something is increasing, something else is decreasing, something could be unconstrained. Here we give integers for those three. And here you can see that we have, for the one that's increasing, they're all positive. For the one that's decreasing, all negative. And for the age, it's unconstrained. And that's just an example. And here we have some partial dependencies. If you look at age, you can see it's monotonically increasing. This one's decreasing. And sorry, that was area, distance, and then age can be whatever. It's not constrained here. So finally, we have this last layer, prediction rigidity, that allows us to estimate uncertainty. And we'll scroll down here, and you can see here we have this monotonically increasing fit, and we have uncertainty going with it, which is pretty convenient. This is the LLPR version, so it is uncertainty, but it is mostly for constant variance noise. It's not, it does not work as well for heteroscedastic noise. So that is what we have there. And then here we have an example of what happens if you ignore these constraints. Let's see. Here we have unconstrained. Still is maybe not monotonic, but you see it has some wiggles in it. All right, this is fully sklearn compatible, so we have a pipeline here. You can use all of the features that you like with scalars, with pipelines, etc., and sklearn. And we get all of these great features of monotonicity, which is useful when you know you need it and you want to be able to guarantee that you get monotonic behavior. So you have some parameters to choose, and these sklearn methods to consider. And I'll put the link to the notebook in the video description so you can check it out later when you want to. All right, thanks for listening to the pycse channel, and we will see you next time with another ML model that has properties that we build in